טוב, אז היום יש לנו את איליה קוטוזוב שייתן את הסמינר דוקטורט שלו. איליה עשה תואר ראשון ושני בבן גוריון בגיאולוגיה, ודוקטורט פה אצל אלון אברני. הוא הולך לדבר על תרכובות גופרית אורגניות במאגרי גז.
טוב, תודה רבה. אז כמו שצחי אמר, הסמינר היום זה בעצם הסמינר דוקטורט שלי. אז טוב, בואו נתחיל. אז היום נדבר על גז טבעי. אז מה זה בעצם גז טבעי? Sorry, I'll switch to English. So today we're going to talk about natural gas. So it's basically a mixture of compounds that are in gas phase at room temperature and pressure. It mainly consists out of hydrocarbons from methane C1 all the way to hexane C6. It could contain condensates and typically contains non-hydrocarbon gases such as nitrogen, carbon dioxide, hydrogen sulfide, and noble gases. As you may have heard, there is a rising global demand for natural gas in the last several decades as more and more power plants are being switched to run on natural gas. And with this increase in demand, there is also a growing interest in the study of natural gas and its different reservoirs. So where does it come from? Well, most natural gas comes from thermal cracking of fossilized organic matter that is called kerogen. It is this kind of huge geopolymer, and it could form natural gas by one of two processes. The first one happens during the diagenesis of sediments, and in this process, microbial activity can consume this organic matter and generate methane as a byproduct. This type of gas is called biogenic gas. On the other hand, if this fossilized organic matter is buried deeper in the sedimentary column to higher temperatures and pressures, it could go through a process called catagenesis and generate thermogenic gas, which contains longer hydrocarbons as well as methane. In addition, natural gas can form by abiotic processes without any organic matter involved. For example, here the Fischer-Tropsch process, in which carbon dioxide or carbon monoxide react with hydrogen and form methane. This type of process takes place in volcanic settings and in hydrothermal vents. But regardless of the gas source, it is important to remember that upon its expulsion from this source to the geological trap where it's accumulated, it can undergo different chemical modifications, which can obviously alter its chemical composition. So why do we care about sources of natural gas? Well, it could be divided into two. Let's say we found a gas reservoir. Our first obvious interest is to find more gas reservoirs and to produce more gas. And for that, we need to figure out what is the source. The second thing is, in order to figure out what is the source, we need to significantly improve our understanding of the local geology and possibly even regional geology. So understanding sources of natural gas is really important. Okay, so we now know that there are different sources of natural gas. How can we distinguish those? As I mentioned at the beginning, the main component of natural gas is hydrocarbons. And over the years, various researchers demonstrated how the molecular and isotopic composition of hydrocarbons can be used to identify sources. For example, in this plot from the work by Milkov and Etiop 2018, they demonstrate how the ratio of methane to longer hydrocarbons versus the delta C13 of methane can be used to distinguish between different sources. For example, in this area we have the biogenic gas, and over here we have the abiotic gas. This plot allows us to to distinguish between biogenic and abiotic gases. In addition, it was demonstrated empirically that this type of correlation could be used to identify different processes that may happen to gas after it was generated. For example, here in green is migration of gas. When gas is migrating from point A to point B in the geological section, longer hydrocarbons, longer than methane, are typically consumed. Therefore, the residual gas becomes enriched with methane, while the isotopic signature of methane doesn't change. Okay, so as you can probably see, there is plenty of overlaps in these fields, and therefore, in many cases, we need more than one proxy to actually figure out what's going on. And sometimes we simply don't have enough stuff to work with. So the general goal of what I'm presenting today is to add a new proxy to this geochemical toolbox that can help us resolve some of the issues you see here and in different proxies. Well, today we're going to talk about sulfur. So sulfur in natural gas is typically in this little part here of the non-hydrocarbon gases. The most abundant sulfur compound in natural gas is hydrogen sulfide. It is a colorless gas that is highly poisonous, flammable, could be explosive under certain conditions, and also highly corrosive to the piping that is used for gas production. So key question here is, can we predict the presence of hydrogen sulfide within a certain reservoir? And the answer is no. If we know the local geology, we can take an educated guess, but in reality, we have to drill it, produce it, and test it. And if for some reason our educated guess was wrong, we could end up in a situation where this highly poisonous compound in natural gas leaks and it has catastrophic consequences. So where does this hydrogen sulfide comes from? We can divide its sources into three. The first one will be thermal cracking of sulfur-rich kerogen. If the kerogen that in first place formed our gas is rich with sulfur, it could generate hydrogen sulfide. This typically happens at temperatures above 60 degrees Celsius and can generate substantial amounts of hydrogen sulfide. And the isotopic signature, the delta S34 of that hydrogen sulfide, will depend on the parent kerogen. Alternatively, hydrogen sulfide can form by microbial sulfate reduction, which is a process in which microbial activity utilizes organic matter and sulfate for its metabolism and generates hydrogen sulfide as a byproduct. This process takes place at lower temperatures, lower than 80 degrees Celsius, generates much less hydrogen sulfide, and the hydrogen sulfide that is generated has a unique isotopic signature. It is typically significantly lighter than the sulfate. The last process that can generate hydrogen sulfide is thermochemical sulfate reduction. In essence, in this process, organic matter reacts with sulfate directly at temperatures higher than 110 degrees, and this process can generate the highest amounts of hydrogen sulfide in the gas. And in this case, the isotopic signature of that hydrogen sulfide will be almost identical to that of the parent sulfate. All right, so hydrogen sulfide is the most abundant sulfur compound in natural gas and the most studied. But there is also another group of compounds that is called volatile organic sulfur compounds. These consist out of thiols that have an SH bond, sulfides that have an S that is connected to two different groups, and thiophens where the sulfur is an aromatic ring. They occur at much lower concentrations, typically ppm or even lower than that. And their presence is not limited to natural gas reservoirs. They also occur at other places in nature. You may encounter them in your kitchen or in the outdoors. They're very easy to identify because they all smell very, very bad. So how do these end up in natural gas? Well, from what we know today, we can point to several processes. The first will be, again, thermal cracking of sulfur-rich kerogen. It was demonstrated in lab experiments that this process can generate these compounds to the gas phase. In addition, cracking of oil to gas can probably also generate these compounds. It was demonstrated by one lab work. In addition, lab experiments and field observations indicate that interactions between hydrocarbons and hydrogen sulfide can form these compounds. Also, over the years, various researchers suggested that reactions between hydrogen sulfide and oil can form these compounds. And the last option is the abiotic origin. This type of source is not really well understood, but there is one work that demonstrated it is possible. Okay, so what do we have so far? We have this group of compounds, the volatile organic sulfur compounds, that are likely linked to kerogens, that in turn can form hydrogen sulfide. Then we have the hydrocarbons, which likely link between volatile organic sulfur compounds and hydrogen sulfide. And there is a likely link between the hydrogen sulfide and the volatile organic sulfur compounds. So all in all, we can say that these compounds, they have a potential in helping us identifying origins of hydrogen sulfide, origins of gas, migration of gas, and maybe other post-generation processes that happened after the gas formed and migrated. The only problem here is that in order to actually use volatile organic sulfur compounds as proxy, we need to understand how each of these processes affects the molecular and isotopic composition of these compounds. And that brings me to my research goals. So what I wanted to do is I wanted to see what is the molecular and isotopic composition of volatile organic sulfur compounds that form when hydrogen sulfide reacts with methane. In addition, I wanted to see what type of volatile organic sulfur compounds form when different types of source rocks undergo thermal maturity and generate natural gas. I obviously wanted to examine naturally occurring volatile organic sulfur compounds from gas reservoirs. And at the end, I wanted to compile all of this knowledge and make this new proxy that will be based on these compounds. So my work is divided into 4 experimental chapters. Today, I'm going to present to you 2 of them. In the first, I'm going to show you what types of volatile organic sulfur compounds form when different rocks go through thermal maturity. And in the second, I'm going to present to you a case study of natural gases from the Ordus Basin in China. And I'm going to show you how we can put these compounds into use. So I'll start with the second chapter. The idea here is fairly simple. Let's take different source rocks, generate natural gas out of them, and see what type of volatile organic sulfur compounds are in the gas. And then what I wanted to do is to see if I can use these compounds in the gas to link the specific gas back to the source rock that generated it. So in order to do that, I needed some rocks. I got 6 samples of source rocks from the United States and China. They range over different geological periods from the Paleozoic to the Upper Cretaceous. But more importantly, they come from different settings of deposition. I have samples from anoxic lakes, regular lakes, marine conditions where anoxia is shifting, it's not permanent, marine conditions where anoxia is permanent, and I have this sample over here, which is of terrestrial environment of deposition. It is basically a coal. So the next stage is to generate gas out of this. And for that, I need this system that is called pyrolysis reactors. In essence, it's a pressure cooker. It has a volume of 100 milliliters. I can put my source rocks inside, seal it, and start heating it up to an experimental temperature. In this case, 300 degrees Celsius, where I hold the experiments for 72 hours. Now, this time and temperature relation was chosen because it mimics thermogenic gas in nature, typically of early maturity stage. Then, at the end of the experiment, I collect the gas that formed into a gas cylinder, and then I go and measure the sulfur isotopes in it. Now, I know it looks a little bit scary, but the system I'm using is called GC, that is coupled to a multi-collector ICP-MS. GC is a gas chromatograph. It is this box over here. The multi-collector is the big box around it. And the way it works is as follows. My gas sample, I inject it to the GC, and then it runs through a column inside of this device. What this device is doing, it basically acts as a filter. It separates the gaseous mixture into separate compounds. Then I can choose my compounds of interest, the sulfur compounds, and divert them from the GC to the multi-collector ICP-MS. There they enter plasma, they become ionized, travel through a magnetic sector, and then I collect the S32 and the S34 isotopes on Faraday cups, and I get the delta S34 value in each specific compound. Now, this method works down to sub-ppm concentrations and has precision and accuracy that is typically better than half a per mil. If you're interested in the method, I suggest you read the Said Ahmed et al. 2017, where the method is described. So let's see some results. Well, first thing that I noticed when I analyzed the gases formed in the experiments was that some contained hydrogen sulfide in concentrations between 0.6 to 4.3%, while 2 other samples didn't generate any hydrogen sulfide in their gas phase. Then I went to analyze the sulfur isotopes, and the result from this analysis looks like this. This is called a chromatogram. Y-axis here is relative response, meaning the higher the peak, the more of the compound we have. X-axis, retention time in minutes. Basically, it means at what time does the compound exits the GC and goes to the plasma. So this sample here has 2.6% hydrogen sulfide. And when I analyzed it, I noticed it has some thiols and concentrations typically up to 18.5 ppm with average isotopic value of plus 10 per mil. And in addition, this sample contained various thiophans, shown here with the orange circles. Their concentration was slightly higher, and they also had a similar average isotopic value. Then I analyzed one of the samples that didn't contain any hydrogen sulfide, and as you can see, something is missing here. And that something is thiols. There are no thiols in these samples, only thiophans. In this specific experiment, the concentrations were lower, and the average isotopic value was again around 10 per mil. So that brings me to a question. Could it be that thiols depend on hydrogen sulfide? In order to test that, I checked the total thiophans concentration in ppm versus the concentration of hydrogen sulfide in each experiment. As you can see, there is a pretty good positive correlation, which may indicate thiols form from hydrogen sulfide. When I did the same thing for thiophans, here presented total thiophans concentration versus hydrogen sulfide, I noticed there is no correlation at all. Okay, so that's this brings me to the idea that thiols do form from hydrogen sulfide, but in order to prove that, I need to go to a concept called isotopic equilibrium. So very shortly, what happens here is like this. If hydrocarbons react with hydrogen sulfide and generate these different volatile organic sulfur compounds, then there is an exchange of sulfur between the hydrogen sulfide and these compounds. Given enough time, the system will achieve isotopic equilibrium. This type of isotopic equilibrium was presented in the work by Amrani et al. 2019, and it is a theoretical model. And in this plot over here, y-axis is large delta, meaning the delta S34 of specific volatile organic sulfur compound minus that of the hydrogen sulfide. As you can see, this relation depends on the temperature in the system. The way it works is like this. Let's go to 100 degrees Celsius and look at methylthiol, MESH. If that methylthiol is in isotopic equilibrium with the hydrogen sulfide that is right there with him in the system, then the large delta between them will be 2 per mil. Otherwise, it is not in isotopic equilibrium. Now, let's go back to my results. So this plot, y-axis is large delta between each separate thiol to the hydrogen sulfide in that experiment. X-axis, different experiments. The dashed line in the middle is the predicted value at isotopic equilibrium. The shaded blue area is plus minus 1 per mil on that prediction of the model. As you can see, some of the thiols are at isotopic equilibrium, while others are fairly close, typically to within 2 per mil from that isotopic equilibrium. So we can say that they likely form from reaction with that hydrogen sulfide. But on the other hand, you can argue, well, what about these thiols over here? They're not in isotopic equilibrium. And in order to understand what's going on here, we need to go to the work by Meshulam et al. 2021, who demonstrated that initial thiols, here's the methylthiol in his experiments. He did synthetic experiments on synthetic compounds and hydrogen sulfide. Initial thiols are far from isotopic equilibrium due to a kinetic isotopic effect. But as the experiment length progresses to 12 hours and 72 hours, the thiols approach equilibrium. Same phenomenon happens to thiophans. Therefore, I suggest that the thiols over here are a result of a kinetic isotopic equilibrium, and if given enough time, they will also approach and achieve isotopic equilibrium. So, what do we have so far? If we have a source rock, and it undergoes thermal maturity and generates hydrocarbons in a gas phase, it could also form hydrogen sulfide. If it does, that hydrogen sulfide will react with the hydrocarbons and form different volatile organic sulfur compounds. These compounds will achieve isotopic equilibrium with that hydrogen sulfide. Also, when we take the temperatures occurring in nature in gas reservoirs, we can say that this large delta will be limited to 1 to 3 per mil. Okay, but what about those thiophans? When we do the same trick with for thiophans, here y-axis large delta and x-axis different experiments, different thiophans are in colors, we see that most thiophans are not in isotopic equilibrium. Moreover, they are far from isotopic equilibrium, and they're also clustered. It's not like we see a kinetic effect over here. And that suggests that thiophans don't form from hydrogen sulfide. We also seen that they occur in all experiments regardless of hydrogen sulfide presence. So the question here is, where do they come from, and what dictates their isotopic signature? Well, the only other thing we have in these reactors is that source rock with that fossilized organic matter, the kerogen. And when I try to link the value of each specific thiophan to the value of the kerogen at the same experiment, I saw that most thiophans are close to the 1-to-1 line, meaning their value is close to that of the parent kerogen. In addition, I added here the hydrogen sulfide in the different experiments just to convince you that it's really what's going on here. Hydrogen sulfide in some experiments is far from the kerogen and far from the thiophans. Sometimes it's close, and sometimes it's simply absent. So this tells us that thiophans form from the kerogen. They preserve the isotopic signature of that kerogen, and that indicates we could probably use them as a proxy. So if we go back to our plot, now we're going to add the thiophans. They formed in all experiments. And we saw that they preserved the isotopic signature of that parent kerogen to within plus minus 5 per mil. I think that with some extra future work, this range will be much narrower. So now I want to show you how we can put this knowledge into use. So I'm going to present a case study of the volatile organic sulfur compounds from natural gases in the Ordus Basin in China. This work was done in collaboration with colleagues from the Institute of Geology and Geophysics of the Chinese Academy of Science in Beijing. So, what is the Ordus Basin? Well, here is a map of China, schematic map. In yellow are the main gas-producing basins. China is a major producer of natural gas. Right here in the middle, we have the Ordus Basin. It is arguably the 5th largest gas-producing basin in China. It is a huge sedimentary basin. The area is roughly 17 times that of Israel. In the beginning, in the beginning, this basin was mainly producing oil. And the first oil well in China was drilled there in 1907. But in the 80s, the Chinese started drilling deeper and reached the Paleozoic section that contained natural gas. As of today, this basin produces natural gas for several large cities, including Beijing. So the samples I'm going to talk about are coming from the Danyudi field. It is a small field in the northern part of this basin. It's producing gas since 1995 and will likely continue to produce gas till 2035. The interesting thing here is that even though it's been produced for more than 20 years, the source of the gas is still not clear. Some studies suggest it comes from Carboniferous coals, others suggest it comes from Permian coals, so it is an open question. So I received 7 gas samples that were collected from the Ordovician Maggiago Formation. It is the main reservoir there. It is a dolomitic reservoir that is capped with anhydrite at its top. The temperature at these reservoirs is 90 to 130 degrees Celsius, and they're buried at 2,000 to 3,000 meters. Some of the gases I received were, all of them were thermogenic. Some contained hydrogen sulfide, while others not. Here in this cross-section, you can see the possible sources, the Carboniferous Taiyuan Formation and the Permian Shanxi Formation. And so, key questions here is, where does this hydrogen sulfide comes from? Why is it in the gas? And also, can we maybe suggest the source of the gas? So just to show you how difficult this question is, we did run the standard gas analysis. It's the same plots I showed you in the beginning. Molecular ratio versus delta C13 of methane. Here is all of our samples. They are between the thermogenic oil-associated gas, late maturity gas, and the abiotic gas. And since there are no claims for abiotic origins in the Ordus Basin, we can rule that one out. And since no oil is produced with that gas, we can suggest that it's late maturity gas from the gas window. Then when we look at the different processes, we can see that the gas is likely affected by migration or maybe thermochemical sulfate reduction, or maybe it even undergoes oxidation. Either way, it doesn't help us figuring out where does the hydrogen sulfide comes from and what is the source. Let's try another proxy. Here we have the delta C13 of carbon dioxide in the gas versus the delta C13 of methane in the gas. Same type of plots. Once again, we see that the gases cluster somewhere between the oil-associated and the late maturity area, so nothing new over here. But when we look at the processes, we now see that the gases may be affected by maturity or mixing or even TSR. Still, it is not clear what's going on here. So that brings me to the volatile organic sulfur compounds. So the first thing I did was I did the molecular analysis of those different gas samples. I could immediately divide them into two. Here is a chromatogram. Once again, relative response, y-axis, retention time, x-axis. I had samples that looked like this. They had very little volatile organic sulfur compounds, mainly sulfides, and at very low concentrations, lower than 2 ppm. I had two samples that looked like that. And I had samples that looked like this. So here you can see sample D18, which contained sulfides, thiols, and thiophens at much higher concentrations. And out of my whole set, 5 samples looked like this. Okay, so the next stage was to analyze the volatile organic sulfur compounds. So this large plot shows you two things. Y-axis is the delta S34 of each separate compound. The different compounds are listed here. And the plot is separated into 4 areas: thiophens, sulfides, thiols, and hydrogen sulfide. I'll start with the thiols. So thiols were occurring in 5 out of the samples I analyzed, and they all show a similar trend, and they all cluster in a relatively narrow range of 6 ppm or lower. When we look at the sulfides, we see a really large spread of the isotopic values. They cover a range of at least 20 per mil. And there is no clear trend over here. It just looks like a scatter. When we look at the thiophens, we see that once again, they're clustered, and they show a relatively narrow isotopic range of 3 per mil or less. In addition, I managed to isolate the hydrogen sulfide out of 3 samples and measure its isotopic values. The values were really close to each other, and they were slightly lighter isotopically than the thiols and the thiophens. So if I have thiols, thiophens, and hydrogen sulfide, and I know the temperatures of the reservoir, we can check for isotopic equilibrium. So here is a plot showing isotopic equilibrium. Y-axis, large delta. X-axis, the different compounds. Shaded area in blue is the area of expected isotopic equilibrium. Since only 3 samples had hydrogen sulfide, I'm only showing these 3 over here. But I'm going to talk about the rest in a moment. As you can see, the thiols of samples D15 and D18 are mostly at isotopic equilibrium. The main sample that is far is the 2-butyl thiol. And sample D17 had isotopic values of thiols that are fairly close to the area of isotopic equilibrium. So for some thiols, they're very, very close. So I suggest that the thiols we see here formed from reaction with that hydrogen sulfide that is in the reservoirs with them. When we look at sulfides, most sulfides are not in isotopic equilibrium. I don't really know why it happens, so that's an open question. Thiophans over here are really far from the zone of isotopic equilibrium. All right, well, that works for only 3 samples. What about the rest? So going to the previous plot, samples D16 and PG27, it's the yellow triangles and this blue open diamonds. They have tiles that are very close to the values of the other tiles. They come from reservoirs of the same formation from similar temperatures. So I argue that these tiles in samples D16 and PG27 formed from interaction with the same hydrogen sulfide. So you may ask yourself, well, where's that hydrogen sulfide now? I suggest that it was removed from the gas phase by reactions with mineral phases, maybe formation of pyrite, which is common. So from the tiles in our samples, we can say that we look for hydrogen sulfide source that have a delta S34, a predicted delta S34, between plus 25 per mil to plus 31 per mil. So let's find that hydrogen sulfide source. So let's go over the different options. First option, thermal cracking of sulfur-rich kerogen. The sources, the proposed sources for this gas, the Permian and Carboniferous coals, have delta S34 of between minus 12.3 to plus 8.1 per mil. It is at least 20 per mil lighter than the hydrogen sulfide we're looking for. It is highly unlikely that it is the source. Second option, microbial sulfate reduction. So current temperature is too high for microbial activity. Microbial activity typically works till 80 degrees Celsius. But the paleo temperature, since the gas entered these reservoirs, was even higher. Therefore, it is unlikely that microbial activity is the source. And that brings us to the last option, thermochemical sulfate reduction. As I mentioned, the reservoirs are capped with anhydrite. And these anhydrites, these Ordovician anhydrites have isotopic values between plus 25 per mil to plus 28 per mil, which is very close to the plus 25 to plus 31 we are looking for. Therefore, thermochemical sulfate reduction of the anhydrites that cap the gas reservoir is the likely source of hydrogen sulfide. And we only had hydrogen sulfide in 3 reservoirs. The other 2 didn't have any hydrogen sulfide. So we could assume it never had hydrogen sulfide. But the tiles tell us a different story. They tell us that the, other reservoirs also experienced thermochemical sulfate reduction. Yeah. But what about that thiophane that we see in our samples? Where did it came from? So I just talked about it. I said that it comes from kerogens, right? So if we look again at the 2 possible sources, the 2 candidates, their isotopic signature of minus 12 to plus 8 per mil, while our thiophanes are plus 29 to plus 32. So this is not the source of the thiophanes. So where do they come from? Well, they have to come from a certain kerogen, and they preserve the isotopic signature of that kerogen. And what that means is that there has to be another organic-rich sedimentary section somewhere buried over there that was previously not considered to be a potential source rock. Can we find this source rock? I argue we can. So let's go through all of the elements of this system we have. We have proposed sources that are Permian and Carboniferous. We know that these gas, or maybe some other gas, reacted with those Ordovician anhydrites in a process called thermochemical sulfate reduction. This process generated what we have today. I'm going to call it our gas. That's what we analyzed. So the key here is our understanding from the tiles of thermochemical sulfate reduction taking place. In this process typically, as I said, organic matter reacts with sulfates, right? So this process typically consumes longer hydrocarbons than methane. And that, in this case, the residual hydrocarbons are enriched with C13 and H2. How it works? Let's say we have these 2 ethane molecules. That's their isotopic composition, H1, H2, C12, C13, and now it experiences thermochemical sulfate reduction. In the residual gas, we're going to have less ethane. And that ethane will be enriched with the heavy isotopes, with C13 and H2. So we can use this knowledge, and so this plot over here shows the delta C13 of ethane versus the delta 2H of ethane. Over here we have in green Permian gases and Carboniferous gases from different studies that studied the gas in this basin. And here is the arrow that points to the general direction of TSR, meaning if these gases experience TSR and formed our gas, then our gas should be somewhere here. In reality, our gas is here smack in the middle. So that immediately tells us that it is highly unlikely the Permian and Carboniferous gas experienced TSR and formed our gas. So where does it come from? Well, I suggest a different story. Here in blue triangles are Ordovician gases from the same Maggiago formation, same reservoirs as our gas, but this comes from a different field where the temperatures are higher and temperatures are lower, and it experienced much less thermochemical sulfate reduction, if any. As you can see, these triangles sit right in the direction where we would expect, if they experience more TSR, would expect the gas form to be somewhere here or here. Anyways, what I'm suggesting, based on the knowledge gained from the volatile organic sulfur compounds, that the source of the gas is Ordovician, and that the kerogen that formed this initial gas has delta S34 between plus 27 to plus 34 per mil, based on our thiophens. So, to conclude, in the beginning I showed you this plot. I told you it has different problems that I want to improve. What I demonstrated so far is the delta S34 of thiophens can be used to identify source rocks of thermogenic gas. In addition, the presence of thiophens in gas can immediately distinguish thermogenic gas from abiotic gas, which I remind you can form only methane. In addition, the presence of thiophens can show us processes of mixing between different gases or between oil and gas. The presence of the thiols in the gas phase and their delta S34 signature can help us identify presence of hydrogen sulfide even if the hydrogen sulfide was removed from the gas, and it allows us to identify the sources of hydrogen sulfide, for example, thermochemical sulfate reduction. In addition, I argue that volatile organic sulfur compounds can be used to identify different pathways, directions of migration of natural gas and hydrogen sulfide, but not necessarily, within a given basin or maybe within a series of reservoirs. So I would like to acknowledge my lab mates. Everything I presented today benefited significantly from the work of Alex Mishulam over here. Lots of this stuff is based on his work, and he really helped me a lot with this work, with both technical aspects, data analysis, everything. I really owe him a lot. And also I was funded by ISF and BIRD. So thank you very much, and questions? Yes, sir.
I guess, or you already said that the temperature that the gas was actually formed is lower than the temperature in the lab, and of course the time frame is much longer.
Yeah.
Can you elaborate how this does?
Yes, I can. One moment. So basically, the way this time-temperature relation works is that it assumes all the different reactions that happen when kerogen is cracking. They go by the Arrhenius first-order reactions, and over the years, different models were proposed to link between time and temperature relations to specific maturity of the gas. One of these models, mainly the one I used in this experiment, is called EasyRO. And it was empirically shown that this model can link between actual values of thermal maturity. In this case, it's called vitrinite reflectance. It's a physical parameter in the different source rocks, in this case in coals. It was demonstrated empirically that the model, the relation that the model predicts, fits pretty good different source rocks. So yeah, I use a model to correlate between the lab experiments to what happens in nature. I think no one knows if it's how accurate is this, but I think the fact that the analysis of naturally occurring gases shows results that are somewhat similar to those of the lab indicates that this method does work. Any other questions? Yes, Aaron.
So you mentioned that the ratio of methane to other alkanes changes during migration.
Yes.
Could migration and the processes going during migration affect the volatile and organic compounds that you're exploring, and also the isotopic ratio?
It's a good question. It's difficult to answer. In different parts of my work, I studied natural gases from Canada that did experience some migration. I think that migration doesn't necessarily affect the volatile organic sulfur compounds. If it does, I assume it will mainly affect the thiols, which are less resistant to general alterations. But the thiophene seems to be very much immune to all sorts of secondary effects, as long as the temperature is within natural temperature. It's not like volcanic settings or something like that. But what we do see clearly is that migration can consume the hydrogen sulfide. It is very reactive, and it is easily removed by reaction with clays or maybe different solutions. Basically, it precipitates as sulfides. So that's all I can say about it.
Well, I'd like to continue from Emmanuel's question. In addition to the geochromatography that you talked about, in the reservoir, how do you differentiate between possible different gases that accumulate into it? Gas is the most mobile fraction.
Yes.
And it is very easily,
Okay. So,
especially on methane.
so within a given reservoir, if all I have is only one reservoir and I know nothing about the local geology, I must assume the gas is homogeneous and it represents that reservoir. If I have a series of reservoirs, for example, as I just presented for the gases from the Ordos Basin, then if all of these reservoirs show somewhat similar properties, I can assume they were affected by similar processes. In addition, I think the key to identification of gas mixing within a reservoir depends on two things. First thing is the geology. You need to know something about the geology that will hint you gases are being mixed. The other thing is that you can use volatile organic sulfur compounds if you can possibly link them to a different source from that generated the gas within the reservoir.
If this is a dry gas, you don't have
If it is a dry gas, if it is, no, yeah, I can present it. Why not? So I'm going to quickly show another chapter. I'll do it really quick. So what I did in this chapter is I took dry gas, methane, and reacted it with hydrogen sulfide at 300 degrees Celsius in the same pyrolysis reactors. the experiments showed that the only volatile organic sulfur compound that forms in this process is methyl thiol. And given enough time, I could see that with experiment length, it approached isotopic equilibrium. Basically, what this tells me is that if I have dry gas and it somehow experienced interaction with hydrogen sulfide, this is the only volatile organic sulfur compound I'm going to find there. And once again, I can use the isotopic equilibrium to actually find the hydrogen sulfide. But to answer specifically your question, if it is a dry gas and it has only methyl thiol in it, I would assume it reacted with hydrogen sulfide. If it has a larger variety of volatile organic sulfur compounds, then there has to be a different gas that was mixed with this gas.